Relative growth rates. Relative rate of growth. I think you'll find this one pretty straightforward. Let's just do a quick review. Graph these things. We have ln of x. It's going to be looking like this. We have e to the x, inverse of it. Y equals x, what they're reflected about. Square root of x. And x squared. Let's go ahead and label these. E to the x, x squared, x, square root of x, ln of x. In general, we've talked about this before, we have our log is going to be less than our power, which is less than our exponential. And what happens when we add in some funny ones like factorial and x to the x? I'll write it out kind of a little bit more generally. Log base a of x, our log, is less than our power x to the b, which is less than our exponential c to the n, which is less than our factorial, which is less than x to the x. And this is where a is greater than 1, b is greater than 0, and c is greater than 1. And recall, x factorial is just x times x minus 1 times x minus 2 all the way down to 1, whereas this is x, 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 so that is bigger. All right, let's look at definition. Let f of x and g of x be positive for sufficiently large, for x sufficiently large. F grows faster than g as x goes to infinity if the limit as x goes to infinity of f over g equals infinity. So in other words, f is dominating g. Another way to look at it is you could say f grows slower than g if this limit is 0. And then f and g grow at the same rate as x goes to infinity if this equals some number L that is not 0. Okay? All right, let's look at some examples. Determine which grows faster or if they grow at the same rate. So we're just going to find limits. Limit as x goes to infinity of 7 over 3 quantity to the x divided by e to the x. So we should simplify this. This can be, they both have the power of x. We can write it as limit as x goes to infinity of 7 over 3e to the x. And since 7 over 3e, the absolute value that's less than 1, this limit is 0. So f grows slower than g. And that's pretty much it with it. So we're just going to look at various different ones. So in this one, we're going to compare 3 different functions. So the first thing we'll do is we'll compare 2 of them, because that's all you can do at one time. We'll check f and g. So we'll say the limit as x goes to infinity of the square root 3x to the 4th plus 5x over x squared. Now we reviewed this in the last section, how to find this limit. Let's go ahead and we'll do it again. Limit as x goes to infinity. We'll factor out that highest power, so it'll be x to the 4th there, and we'll have 3 plus 5 over x cubed over x squared. Take it out. We get limit as x goes to infinity of the absolute value of x squared, but does the absolute value have any effect on that? Nope. Since x squared is always positive anyways, and we can reduce those to get the limit as x goes to infinity of the square root of 3 plus 5 over x cubed. Let me make sure everything's in. And so that's going to be just the square root of 3. So we look up, since it equals some number that's not 0, this says f and g grow at the same rate. Let's look at, we can compare f and h, or we can compare g and h. G and h looks easier, so let's go ahead and do that one. So we'll have the limit as x goes to infinity of square root 2x to the 4th minus 3x squared divided by x squared. Now, since what we talked about before up here, square root of x squared, square root of x to the 4th equals x squared. This is for all values of x. We're going to go, and instead of doing it like I did the first one, I'm going to take and I'm going to bring this x squared, and we're going to make it as one radical. Give you another way to do some of these things. 2x to the 4th minus 3x squared, all divided by x to the 4th. So that is, the limit as x goes to infinity of, go ahead and do that division, 2 minus 3 over x squared, and that will equal square root of 2. So what does that mean? That says that g and h grow at the same rate. So what does that mean overall? That f and g and h grow at the same rate. Using the transitive property. Grow the same rate. Recall the transitive property says, you can say if a equals b and b equals c, then a equals c. So if f grows at the same rate as g, g grows at the same rate as h, f grows at the same rate as h as well. All right. Next one. At this point, it's a matter of finding a bunch of limits. And it's trying to bring in a couple of ideas that just review to make sure our skills are good with it. So we'll bring down that 1/2. So we'll have 1/2 log base 5 of x over 2 ln of x. Let's say so this will be 1/2 over 2, so that'd be 1/4. Let's convert, use a change of base, log base 5 of x. So we have 1/4, and then we have ln, and we'll convert that to natural log over natural log of x. Actually, I messed that up, didn't I? Let me put x over natural log of 5 divided by natural log of x. So this gives the limit as x goes to infinity of 1 over 4 ln of 5. So what does that equal? 1 over 4 ln of 5. There is no variable in it. It's a constant. So what does this mean? F and g grow at the same rate. Next one. Say the limit as x goes to infinity of x minus log base 2 of x over natural log of x. So what we could do is we could manipulate it, and we could use the ideas in number 1 above. But if we're plugging this in, we can also realize that this is end up going to be infinity minus infinity over infinity. Let's go ahead and use L'Hopital's. And that's not 100% clear here, this infinity minus infinity. Will that be it? But x does dominate it. And I'm still kind of using that idea. So I'd have here the derivative of log base 2 of x would be 1 over ln of x times x. I'll put the x first just to make it clear. Times 1 over x. Limit as x goes to infinity. Right over here. for the room. Go a little bit, zoom in a little bit more. So we go into infinity of, let's flip and multiply by the x, so we'll have x minus 1 over ln of 2, and that is going to infinity. So since that goes to infinity, f grows faster than g. All right, next. On this one, it's just to say, do you know how fast things are growing? Can you recognize it in different forms? So when I look at this, I have an exponential, I have a polynomial, a power function, I have a log, and I have an exponential, but let me transform that and just make it 2 cubed to the 8, to the x, so 8 to the x. So at this point, we should just be able to write it down quickly by just looking at it. We know ln of x to the 5, which is the same as 5 times ln of x. That's the slowest. Comma, we have x cubed. Actually, maybe I'll just write it this way. It's less than, that'll be less than 3 to the x in exponential, which is less than 8 to the x, since that's also an exponential. That will be less than ln of x to the x, which will be less than x to the x. And if you're not 100% clear on looking at these types of these last parts, you could say to yourself, they're all raised to the power of x, so what's bigger? 8 is going to be less than ln of x after you get to some point, which will be less than x. So that's it. All right. Big O order and big O notation. Make sure you can see that. All right. Let f of x and g of x be positive for x sufficiently large. Then f is of smaller order than g as x goes to infinity if the limit is f over g equals 0. You write it as f equals, this is a little o, and the way it's said is f is little o of g. F is little o of g. Then we have f is at most the order of g as x goes to infinity if there's a positive integer m for which f of x over g of x is less than or equal to m for sufficiently large x, so as x is getting big. And the way we're going to write this one is f equals big O, and you say on this one f is big O of g. Now this is used in computer science to compare how fast a search is. So your typical performance are looking at big O of n squared, or big O of n log n when you're dealing with different sorting. So an insertion sort, a selection sort, a binary sort, merge. You could also look in, I think Python deals with, their standard is a Tim sort, which will range between big O of n and big O of n log n. All right. Determine whether the statement is true or false as x goes to infinity. So x equals little o of 1 over x. So what we'll do is find the limit as x goes to infinity of x divided by 1 over the quantity of x plus 2. Since I'm writing this as a diagonal fraction, make sure that you have your parentheses there. Simplify, we have the limit as x goes to infinity of x times x plus 2, and that is infinity. So is it little o? No, because it's infinity, so this is false. Square root of x log base 5 of x equals little o of x. So we'll have the limit as x goes to infinity of square root of x log base 5 of x divided by x. If we manipulate this down, square root of x divided by x will be root x in the denominator. And then log base 5 of x will be the natural log of x divided by the natural log of 5. So now, there's a couple ways we could go about doing this. We could say, if we were basing this on problem number 1, what is going to grow faster, log or this power function? Well, the power function is going to grow faster, so this means this is going to go 0. So based on number 1. So let's say you forgot about that, though. You could say, if you're going to infinity, you have infinity over infinity, so we could use L'Hopital's. So we'll have limit as x goes to infinity of 1 over x divided by 1 over 2 root x, and ln of 5 is just a constant. So if we simplify this, we get x goes to infinity of 2 root x divided by x natural log of 5. Limit as x goes to infinity of 2 over root x natural log of 5. And that is 0 as x goes to infinity. So either way is fine. Remembering our L'Hopital and when to use it is a good thing, though. All right, number 9. At this point, you just need to practice. And that's all that I'm doing here. There's just various different ones, various different situations on how to deal with them. So we have limit as x goes to infinity. Let's simplify this fraction to 1 plus x cubed over 3 to the x. As x goes to infinity, we have 1 here. Now we could treat it separately and say this is infinity over infinity and use L'Hopital's, but this is a polynomial over the exponential. That's going to 0. So this goes to 1. So this is true because it is, oh, I never answered the first one completely, or I shouldn't say first, number 8. This is true because that gave 0. All right, number 10, though, is a little different. This one we'll have to treat a little differently, and we need to understand what that second rule for at most is saying to us. So we're going to find this limit. Now, what can you guarantee about cosine of x? Cosine of x is always less than or equal to 1. Actually, I don't even need to worry about that absolute value there. We can just guarantee that it will never be greater than 1. So when we look at this first one, all we need to do is bound it. We need to find some number where this thing can't be bigger than. So we can say this is going to be less than or equal limit as x goes to infinity of 4 plus, if we just treat cosine of x as 1, this would be 4 plus 3 over 4. And now that's just a constant, so that equals 7/4. So this is true because we've bounded it by 7/4. That fraction will never be bigger. All right, next one. The limit as x goes to infinity of ln of 3x divided by ln of x quantity squared. We can manipulate ln of 3x. Let me make it a little bit bigger. And we can say that that's the same thing as ln of 3 plus the ln of x divided by the ln of x quantity squared. So if we break this up into two separate fractions, we'll have ln of 3 divided by the ln of x quantity squared plus the ln of x divided by the ln of x quantity squared, but that's going to reduce to 1 there. And now we have, as x goes to infinity, the first part is going to 0, and then we have 1, and the second part's going to 0, so this whole thing is 0, so that is true. Because all we need to say, is it bounded by a number if it goes to 0? Yes. And the last one, the limit, make sure everything got there, the limit as x goes to infinity of 9 to the x over 9 to the x over 2. We could say the limit as x goes to infinity. We have the same base, so we can say this is 9 to the x over 2. Or you could go ahead and simplify that to square root of 9, which would be 3 to the x. Either way, it doesn't really matter. This is going to infinity, so this is false. And that is all for our big O, little o notation.